Alright, so I wanted to show a connection between logarithms and how complex numbers work. I. Particularly I. Alright, so I've shown before that things like, 2 to the cube, 2 to the third, 2 cubed, right, is most properly viewed as 1 times 2 3 times. Alright, so there's 3 multiplications by 2 of an initial 1. 2 to the 0 is 1. 2 to the negative third, we're doing the opposite of multiplying, so we're dividing repeatedly. And assume there's parentheses is appropriate there. So it's 1 divided by 2, and then that divided by 2, and then that divided by 2. Right. Okay. So we can sort of look at this like, okay, there is... Woo! My hand caught the, accidentally caught the camera cable. Alright. So then you can do fractions, right? So like 2 to the 1/2 is 1 times some value where 2 to the first is this. Alright, so what we've here to get 2 to the first power, which is 2, we have to multiply 1 by this value twice to get there, right? Which means that this has to be the square root of 2. Okay, so you can graph this, you can think of this way, right? So here's your starting point. Your starting point is 1. Here's your goal is 2. And then in the middle, you get your square root of 2, right? So when we multiply this by the square root of 2, we get here. We multiply this by the square root of 2, we get here. The next one, so we're making these evenly spaced. These are even distances, right? So here we're going to have 2 root 2, and here we're going to have 4. Right? So this is our 0th. This is our first power of 2. This is our 1/2 power of 2. This is our second power of 2. And, the third would be 8, right? Here we've got our 3/2. I'm not sure how you would say that. But we can go to the negative too, right? Because this is 0 and then this is in the positive direction. So we can break it out into the negative direction, right? And here, what is this going to be? It's going to be 1 over root 2, which you may be slightly more familiar with as root 2 on 2. But this is our negative 1/2. And then if we go another one out, we're going to get 1/2. Right? So this is our negative first. Right? So that will continue that way. That continues that way. Okay, so how does this relate in any way to I? Well, first off, let's notice that if we were to rescale this to like the way we normally would draw out a number line, the distance between these should be half the distance between these. But here it's the same distance, right? It's the same exact distance because what we're considering to be a half operation is different than if we're looking at a normal number line. And you can actually analogize this a little bit further. If our operation is incrementation, then going from 3 to 6, right, doubling it, won't really... kind of depends how you look at it. It depends how you draw it out. But with addition, you can just do one operation. You can just add 3. With incrementation, you have to do multiple operations, so it's further away. Right. Same kind of thing here, right? We can get to much larger numbers with a smaller number of steps, sort of thing. Okay. So let's just take kind of a regular number line again. Here's our origin. This goes off to infinity. This goes off to negative infinity. This will be our, say, reals, whatever you want to call them. All right. Now, our reference is 1 and -1. And we want we want the square root of -1. So what's going to happen is we need to find a halfway step between 1 and -1. It's going to act like this, right? So we've got here's 1. Here's -1. What does the square root of -1 look like? Alright, how do we get there? That's what we're trying to do. We're trying to go from our 0th term, which is 1, to our first term, which is the square root of -1. Or our first term is -1. Sorry. And our half term is the square root of -1. So we're trying to get halfway there via multiplication. Well, it definitely doesn't exist here in this dimension. Okay? Which means it must be perpendicular. It must exist in a perpendicular dimension, and it doesn't really matter where we put it. There you go. And now, actually, if you look at this, it visually makes quite a lot of sense, because we go some distance, and then we go exactly the same distance again. It looks just like this, sort of, except that we had to go into a perpendicular dimension in order to get at it, because it doesn't exist in the dimension that we're operating in. But it really does look a lot like this. One of the differences, though, is here we are playing with numbers. Right, so we're 1, 2, 3, 4, right? This is the numbers that we're messing with. Here, we're playing with units. Right, because what we're doing is we're actually transferring between dimensions in order to get this to happen. Dimensions are units, right? That's what a dimension is. A dimension is a type of unit. It's like the dog dimension, the feet dimension, the miles, the pounds, whatever your units that you're working in. The LeBron James dimension, right? How many is LeBron James in the room? If it's yes, then hey, we have a member of the LeBron James dimension in the room, right? That's what units are, right? So here, what we're doing is we're playing with units, and here we're playing with numbers, and that's one of the fundamental reasons that this is weird. It's also worth noting that there is an infinite number of dimensions that are perpendicular to this one, which is why you can get things like quaternions. There's where I, j, and k are all the square root of -1. Because, yeah, you can have as many as you want. You can, any number, they're all the square root of -1. Anything that's perpendicular to this, the base unit of that dimension is the square root of -1. Because all you have to do is pass through there. Boom, boom. And you get, via multiplication, and you'll get to -1.